Hello and welcome to Tribe Topper. In this video session, you are going to learn about potential divider. A potential divider is just an arrangement which is used with sensors to produce a variable potential difference. Like, for example, let's say we have a sensor in the automatic lights which automatically light up during the evening when it's dark. So that means there is some sort of change in the potential difference happened which turns on the light automatically. Or it is also used as a sensor where it gets affected by temperature, like in the fire alarms. So that circuits which are using the automatic sensors, they use this potential divider. So the most basic potential divider actually consists of two resistors. One is the resistance R1, which is fixed. This is your resistance R1, that is a fixed one, and R2, which is a variable one. These two are connected in series with a power supply. So as you can see here, there is a V input as the input voltage, and it is supplied to these two resistors R1 and R2 connected in series, where R1 is a fixed resistor and R2 is the variable one. So this arrangement is used to provide a fixed potential difference somewhere between 0 and EMF of the power supply. So whatever EMF we have supplied, it should be able to provide us a potential difference equal to that. So let's apply the combination of resistors in series thing here. So we have a total input voltage V in, which gets divided as V1 and V2. V1 across the first resistor, this one, it will take V1, and the other one is going to be V output, which is V2. So the total voltage V is going to be I times R. Therefore, the current I that flows in the circuit, here the current I enters, the same current will flow through the first resistor and then through the second resistor. So that current I is equal to V, the applied potential difference, over R, where R is what? It's the total potential, it's the total resistance. So that's going to be R1 plus R2, because R1 and R2 are in series. So let's put this value of R here. Therefore, we would say the current that flows in the circuit is V upon R1 plus R2. So what will be the current across each resistor? Therefore, the current across the first resistor R1 will be equal to V by R. So that's going to be I is V by R1 plus R2, and the same current flows across R2 as well. So what is the potential difference that exists across R1 and R2? That is going to be different in series. So we'll say therefore V1, the potential difference across the first resistor, which is a fixed resistance, is IR1. So that's going to be I, which is V over R1 plus R2, times R1. And the second potential difference V2 will be IR2. So that's going to be V upon R1 plus R2 times R2. So now when we look at these expressions, we find out one thing, that like this particular diagram that we have taken here, my variable resistor is a thermistor. So thermistor is the one which has a very high resistance at lower temperatures. So at low temperatures, the resistance of thermistor is high. And since the resistance of thermistor is high, so what can you say about the potential drop across the thermistor? Of course, that will also be high. So therefore, potential drop across the thermistor is high. But as the temperature rises, that's the purpose of a sensor, right? So when the temperature rises, the sensor should detect it. So as the temperature rises, the resistance of the thermistor falls. And when the resistance of thermistor falls, what happens? The resistance of the thermistor falls. Therefore, potential difference across the thermistor is now less as compared to the potential drop across the fixed resistor R1. So across the fixed resistor R1, now the potential drop increases, and the potential drop across the thermistor decreases. So immediately the sensor detects this change, and as soon as it detects this change, it activates the fire alarm. Right? It activates the fire alarm. So the rise in temperature is sensed because of the fall in the resistance, and the fire alarm gets activated. So this is how the sensor circuits work. Okay, now let's have a look at this question that a light sensor consists of a 6-volt battery, an 1800 ohm resistor, and a light dependent resistor all in series. When the LDR is in darkness, the potential difference across the resistor is 1.2 volt. So let's figure out. They say calculate the resistance of the LDR when it is in darkness. They say when it is in darkness, the potential difference across the potential difference across the resistor, that is say V1 across the fixed resistor, is 1.2 volts, and the total potential difference that has been applied by the battery is 6 volt. Therefore, what will be the potential difference across the LDR at this time? Across the LDR, the potential difference would be 6 minus 1.2. So that is 4.8 volt. Now we have to calculate the resistance of the LDR when it is in darkness. For that, we have the voltage, but we would also need the current through the LDR. The current is going to be same whichever is going through the fixed resistor of 1800 ohms, because the fixed resistor 1800 ohms and the LDR, they are in series. So whatever current enters this resistor, the same current flows through the other resistor. So let's find out what's the current through the fixed resistor or 1800 ohm resistor. The current through the 1800 ohm resistor using Ohm's law, since V is equal to IR, therefore I is equal to V by R. So the potential difference across that fixed resistor is 1.2 volt. So 1.2 upon 1800, and that gives me a current of, so it is 0.67 milliamperes. Now we have the current that is flowing across the LDR, because the same current will flow through the LDR. So we can find out the resistance of the LDR in darkness. Hence, the resistance of your LDR in darkness will be equal to, since V is equal to IR, so R is equal to V over I. The potential difference across this is 4.8 over the current is 0.67 milliamperes. So we get the resistance to be 7200 ohms. And in the B part, they say when the sensor is in the light, its resistance falls to 2400 ohms. So calculate the potential difference across the LDR. Now see, whatever is the ratio of the resistances of the LDR to the fixed resistance, the same will be the ratio of the potential difference across the LDR and the fixed resistance. Now the ratio of resistance across LDR upon, we would say, resistance across the 1800 ohm resistor, that is equal to 2400 upon 1800, which gives 1.33. Now therefore, the ratio of the potential difference across LDR upon the potential difference across 1800 ohms should also be 1.33, and for that it is going to be, the potential difference across LDR would be 3.4, and the potential difference across 1800 ohms will be 2.6. So this ratio would also be 1.33. So potential difference across the LDR should be equal to 3.4 volts, so that the total sum is still 6 volt, and the ratio is the same as the ratio of the resistances, which is 1.33. So that's all in this video session. In the next video session, you are going to learn about Kirchhoff's laws. Thank you.